Welcome everybody to this new lecture of our paper Waves, Oscillation and Acoustics. Today we will continue our discussion over the energy of harmonic oscillator, and in our previous lecture we were discussing about the kinetic energy, potential energy, total energy of harmonic oscillator, and the total energy of harmonic oscillator is coming out of this form, that the total energy E total is equals to half ma square omega square, which is a constant quantity, and this is the consequences behind this formula, that the total energy of a simple harmonic oscillator or a particle which performing SHM is proportional to its peak amplitude square and also proportional to the frequency of that harmonic oscillator. Okay, now continue this discussion. Let us see the maximum kinetic energy. What is the maximum kinetic energy? And the kinetic energy is given by this relation. Kinetic energy is given by this relation, equation number 15. That is, kinetic energy is half ma square omega square cos square omega t plus phi. This is equation number 15. Okay, now we are talking about the maximum kinetic energy. Okay, so the maximum kinetic energy is when the value of cos omega t plus phi is equals to 1. Anything in the angle of cos or anything in the angle of sine, these two quantities, these two trigonometrical ratios, cosines and sine, has a maximum value equals to 1 and has a minimum value is equals to -1. Okay, so this kinetic energy, this form of kinetic energy, this given by equation number 15, is maximum when this term cos square omega t plus phi has the value, okay, not square but cos omega t plus phi has value +1. Okay, and square of that value gives nothing, that is square of 1 gives you 1. So the maximum kinetic energy from this relation, equation number 15, is coming out half ma square omega square. This. So the maximum kinetic energy, is equals to half ma square omega square. Okay, and what about maximum potential energy? Because the potential energy is given by this equation number 16, and which is equals to half m omega square a square sine square omega t plus phi, and same thing, sine omega t plus phi has maximum value equals to +1. Put here +1. So square of +1 is 1. So maximum potential energy from equation number 16 is potential energy maximum is half ma square omega square or m omega square a square, whatever you want to write. Okay, so maximum potential energy is this. Maximum potential energy is half ma square omega square. Okay, so look at these two relations. Maximum kinetic energy is half ma square omega square, maximum potential energy is half ma square omega square, and one thing that the total energy is also half ma square omega square. Oh, this is the very interesting fact, that maximum potential energy is equals to maximum kinetic energy and will be equals to the total energy of that harmonic oscillator. This is very interesting fact. Okay, so the maximum kinetic energy is equals to the maximum potential energy. Look at these two relations. Okay, and will be equals to the total energy of harmonic oscillator and is equals to half ma square omega square. This is the graphical representation of energy. These lines, this straight line is represented the total energy, and this line, this parabolic graph, this is reverse. Actually, this is a reverse parabolic graph is represented the kinetic energy of harmonic oscillator or any particle which performing SHM, and this parabolic graph is represented the potential energy of that particular particle or that particular harmonic oscillator. Okay, on this axis there is displacement, and on this axis there is energy. Okay, and you first look at the kinetic energy. This is the displacement. This is the maximum displacement at positive side, and this is the minimum displacement at negative side. Okay, so when the displacement is maximum, the kinetic energy is minimum. Displacement is maximum, that means kinetic energy is minimum. And when displacement is minimum, that is equals to 0, the kinetic energy is maximum. The kinetic energy is maximum. And the reverse of this, that is reverse of this thing is true for potential energy. That is, when the displacement is maximum either on positive side or at negative side, the potential energy is maximum. The potential energy is maximum. And when the displacement is minimum, that is equals to 0, the potential energy is minimum, that is 0. So this is the graphical relation between the energies of simple harmonic oscillator, and this line, this straight line represented the total energy, which shows that the total energy of harmonic oscillator is constant. It is now changed with amplitude, variations in the amplitude actually. So this is the graphical representation of energy of a simple harmonic oscillator which performing SHM. Oh, now talking about the same topic, but this is quite different. That the time averages of kinetic energy, potential energy of a SHO, that is S stand for simple, H stand for harmonic, O stand for oscillator. That is the time averages of kinetic energy and potential energy of simple harmonic oscillator. Okay. Now, the kinetic energy of a particle performing SHM is given by this relation. Okay. We know that this is the equation number 15th of our last topic. The kinetic energy of a particle which performing SHM is given by this equation, half ma square omega square cos square omega t plus phi. Okay. Now, the average kinetic energy. What is the average kinetic energy? The average kinetic energy over a complete cycle or a whole time period. एक पूरी साइकिल कंप्लीट करने में, एक चक्र पूरा करने में, उस सिंपल हार्मोनिक ऑसिलेटर को, चाहे वो किसी भी तरह का सिस्टम हो, एक मैकेनिकल सिस्टम हो, जिससे मैकेनिकल सिस्टम का मतलब ये है कि आप कहीं एक सिंपल पेंडुलम के साथ डील कर रहे हैं, कंपाउंड पेंडुलम के साथ डील कर रहे हैं, टॉरिजन पेंडुलम के साथ डील कर रहे हैं, या फिर कोई वो इलेक्ट्रिकल कोई अरेंजमेंट है जो सिंपल हार्मोनिक ऑसिलेशन का एग्जांपल, जैसे एलसी सर्किट के बारे में हम आगे चल के बात करेंगे. तो एक कंप्लीट साइकिल, ये मीन्स a positive half cycle and included a negative half cycle, which is the complete half cycle, which says as the complete cycle of that particular SHO or particle which performing SHM. So kinetic energy average this time. This is the kinetic energy, but average this time. So the formula of calculating average, any average is 1 over t. T is the time period, and time period is defined as the time taken by the particle to complete one cycle, or time taken by the particle to complete a full cycle. So this is time. So 1 over time period, and limits is 0 to t, kinetic energy dt. This is the familiar formula of calculating averages of any sinusoidal type wave which repeated its cycle after a definite time interval. Okay, so SHM is like that motion, like sine wave, like cosine wave. Okay, so simple harmonic motion is very much similar to that. So kinetic energy average is 1 by t 0 to t kinetic energy dt, and you know that the value of kinetic energy is half ma square omega square cos square omega t plus phi. So put here kinetic energy this dt. Okay, and what are the constant quantities? Half is constant, mass is constant, amplitude is constant, omega square frequency is constant, angular velocity is constant. So these all terms is coming out of the integration, and this term will be ma square omega square this over 40, because we multiply and divide by 2. Okay, when we divide by 2, this 2 is converted into 4, and this 2 is into the denominator by the multiplication. Okay, by the multiplication factor. So 2 cos square omega t plus phi dt, this 2 cos square theta can be written as 1 plus cos theta, 1 plus cos 2 theta actually. So this quantity is constant, integration 0 to t is same, and this is converted by the trigonometric relation 2 cos square theta is equals to 1 plus cos 2 theta, or cos 2 theta can be written as 2 cos square theta minus 1, this minus. So when you calculate 2 cos square theta, so this can be written as 1 plus cos 2 theta, that is here theta is omega t plus phi, that's why 1 plus cos 2 omega t plus phi into dt. Okay, and now writing these two terms into different integrations, that is this term is same 0 to t dt, this one is multiplied by dt 0 to t dt plus cos 2 omega t plus phi dt, this term this, and when you integrate this term over a whole cycle 0 to t gives you the result 0, or this mathematical calculation gives you 0, because the average value of sine or cosine function over a complete cycle is 0. So this mathematical function gives you 0, and if you integrate this dt gives you t. So actually the kinetic energy, average kinetic energy, time average of kinetic energy is equals to ma square omega square over 40, this, and t is coming from this integration. So t is cancelled with t, and we are left with ma square omega square, this. And look at this relation. This is the average kinetic energy, ma square omega square over 4, and look at here, maximum kinetic energy is half ma square omega square. Okay, so actually this relation is equal to, can be written as the half of half ma square omega square, and that is equals to half of maximum kinetic energy. That means the average kinetic energy, the average of kinetic energy is half of maximum of kinetic energy. This is the result we obtain by the time average of this kinetic energy. Now talking about the average potential energy. What is the average potential energy? Okay, so you know that potential energy is given by this function. This is given by equation number 16 of last topic, this equation number 16. The potential energy of a simple harmonic oscillator is half ma square omega square sine square omega t plus phi. This is equation number 16. Okay, so what is the average potential energy? So average, the simple thing, the average of potential energy of the particle over a complete cycle or whole cycle for a whole time period is given by potential energy average, and the same thing as we calculated here. This average kinetic energy, average potential energy this time. So put this function here, put this function here. Okay. Now same thing, the constant quantities are coming out of the integration, and we are left with only the t function, dt type function, because integration is with respect to small t. So all the constant quantities are coming out of the integration. Okay, let's see it. This. So the average potential energy is equals to ma square omega square over 40. This is a constant quantity. Multiply by 2, divide by 2. Divide by 2 makes 4 here, and multiply by 2 is here. 0 to t 2 sine square omega t plus phi dt. This 2 sine square theta gives you 1 minus cos 2 theta. The simple mathematical trigonometrical relation. Sine 2 sine square theta gives you 1 minus cos 2 theta, and here is theta is omega t plus phi. That's why here is omega t plus phi. Okay, so this relation, this trigonometric relation, convert to this trigonometric relation by the simple formula. Okay, now writing these two terms with separate integration. So ma square omega square over 40 is out of the integration, same as the above terms, and 0 to 2 dt this, and minus 0 to t cos 2 omega t plus phi into dt this, and look at this term again, this, and look at here, this 0 to t cos 2 omega t plus phi dt. This mathematical calculation gives you 0. So why this mathematical calculation also gives you 0? Because the average value of sine and cosine function over a complete cycle is 0. So when you integrate this dt between the limits 0 to t gives you t. So the average potential energy is equal to ma square omega square over 40, t is cancelled with t, and which gives you ma square omega square over 4. And the same thing here. This, look at the maximum potential energy. This is the maximum potential energy is half ma square omega square. Okay, and look at here, ma square omega square over 4. That is, the average potential energy is equal to the average kinetic energy and is equal to half of maximum potential energy or maximum kinetic energy. Okay, so this, and this can be written as half ma square omega square, which is the average potential energy and also the average kinetic energy of the particle, and which can be written as half of half ma square omega square, and which is the total energy of simple harmonic oscillator. So this is the total energy of, that is half of total energy. You can say it that average potential energy of a particle which performing SHM or average kinetic energy of a particle which performing SHM is half of the total power of that particle which performing SHM or that particular harmonic oscillator which performing SHM. This, that is half of total energy of the particle of which performing SHM. This. So this is all about the time average of energy of simple harmonic oscillator or a particle which is performing SHM. So now moving to next one is example of SHM, and this topic is included in your syllabus as the mechanical and electrical system, which constitute SHM. So These are some examples like simple pendulum, compound pendulum, or LC circuit. So like the example like simple pendulum or compound pendulums are the mechanical system which performing SHM, and the circuit like LC circuit is the electrical system in which there is the phenomena of SHM there. Okay, so talking about first mechanical system according to your syllabus, but this is simply some examples of SHM, nothing new in this. Simple pendulum, सरल लोलक, इसके बारे में आपने अपनी 12th लैब में कहीं ना कहीं ज़रूर एक्सपेरिमेंट किया होगा, अगर आपके यहाँ लैब थी तो, और हमने अपनी लैब में भी when were the colleges are opened, तो अपनी लैब में भी हमने सिंपल पेंडुलम का एक एक्सपेरिमेंट करके देखा था और कुछ बच्चों ने वो परफॉर्म भी किया था। तो सिंपल पेंडुलम होता क्या है कि एक हमारे पास एक डेंस मटेरियल का एक गोला होता है जो कि एक धागे के द्वारा किसी दृढ़ आधार में बंधा रहता है और it is free to oscillate around its mean position, and that arrangement is known as simple pendulum. Okay, तो सिंपल पेंडुलम में एसएचएम का जो फिनोमिना है उसको हमें समझना पड़ेगा और किस तरह से सिंपल पेंडुलम में एसएचएम की फिनोमिना होती है वो बात भी हमें सीखनी पड़ेगी। सो व्हाट अबाउट सिंपल पेंडुलम, लेट्स सी। Okay, so simple pendulum. A simple pendulum is a heavy particle, ideally a point mass, suspended by an inextensible and weightless, the two thing, inextensible and weightless string from a rigid support. एक किसी दृढ़ आधार से बंधी एक ऐसी धागे से, एक रस्सी से जो इनएक्सटेंसिबल हो और वेटलेस हो, इनएक्सटेंसिबल हो और वेटलेस, दोनों बातें। तो ऐसे एक सिस्टम को, ऐसे एक पार्टिकल को विच सस्पेंडेड बाय एन एक्सटेंसिबल और वेटलेस स्ट्रिंग is known as, by a rigid support, is known as simple pendulum. So let S be the point of suspension and O the mean or equilibrium position of pendulum, that is of bob. This pendulum, the point mass you can say it as, say as bob or known as bob. Suppose the bob is displaced through an angle theta, then the weight mg acting downwards exert a torque, and that torque is equals to minus mgl sin theta. Look at here. This is the arrangement of performing SHM in simple harmonic performing simple harmonic motion in this simple pendulum. This is the pendulum, and this point mass is known as bob. This is this equilibrium position which is at rest, and this is the rigid support by which this pendulum is suspended by an inextensible and weightless string. Okay, and say when this pendulum is displaced by an angle theta, this angle theta, this. So the situation is there that in this situation this is in equilibrium position, and when this bob is at this position A, then this angle will be theta. That is, this bob is displaced by an angle theta and weight mg is acting downward, but the weight mg is downward and this exert for a torque mgl sine theta. This, because this length is L sine theta and the weight is, this weight is mg, so the torque acting upon this bob is mgl sine theta. Okay, torque is simply a force which try to move an object in circular motion, not in straight path, not in straight path. Okay, that is a simple definition of torque. Okay, torque is a, you can say it as rotating force. Simple, nothing less, nothing more. Torque is a rotating force. Try to rotate an object. So try to rotate it. This, and this negative sign indicates that the torque is oppositely directed to the displacement theta, angular displacement theta. This. Okay. Now if d2 theta over dt square be the acceleration of the bob towards O, and I be the moment of inertia about the suspension, and is perpendicular to the plane of paper, the moment of force, that is torque, acting on the bob is given by I d2 theta over dt square. This. The moment of force, that is torque, is given by I, the moment of inertia about the point of suspension, and this angular acceleration d2 theta over dt square. This. Okay. So this is the torque and this is also the torque. So on comparing these two results, we have I d2 theta over dt square is equals to minus mgl sine theta. And from here we can calculate d2 theta over dt square is equals to minus mgl over I into sine theta. Okay, since moment of inertia of the bob about the point of suspension is ml square. M, mass, into this length, L, square of this length. This. Performing SHM like this, like this, like this. Performing SHM like this. And moment of inertia is mass and the square of the distance from the point of suspension, that is L, the length of this inextensible and weightless rod, weightless, you can say it as string. This length, L. Okay. So the moment of inertia about the point of suspension, mass into the square of distance from the point of suspension. I is equals to mr square. Simple formula. We studied this formula in our syllabus of mechanics. Okay. So d2 theta over dt square simply mgl by I, which is into sine theta, and I is ml square. So d2 theta over dt square is mgl over ml square sine theta. M is concealed with m. 1 power of L is concealed with 1 power of L, and is equals to minus z by L into sine theta. Minus z by L into sine theta. And let's say it as mu, this g by L factor, this as mu into theta, because assume that this angle is very small. This angle is very small. That's why sine theta can be written as theta, and this quantity g by L is written as mu, where mu is equals to g by L, which is the acceleration per unit displacement. Gravitation acceleration per unit displacement. See, if L is equals to 1, then mu is equals to g. That's why the mu is defined as the gravitation acceleration per unit length. This gravitation acceleration per unit length. Okay, this mu is equals to g by L. If L is equals to 1, then mu is equals to g. So you can define mu as gravitational acceleration per unit length. Gravitational acceleration per unit length. And simply you can say by this relation that d2 theta over dt square is equals to minus mu into theta, and mu is a constant because G is a constant at Earth's surface, and L is constant because this is in an inextensible and weightless weightless string. So you can say it as d2 theta over dt square is equals to minus mu into theta, and mu is G by L. G by L is constant, so mu is constant, and that's why d2 theta over dt square is directly proportional to minus theta. And what is theta? Theta is the angular displacement. Okay, so the angular acceleration, this of the bob, is directly proportional to angular displacement and is directed towards its mean position, this suggested by this negative sign. Angular acceleration of the bob is directly proportional to the angular displacement theta, and this minus sign suggests us that it is towards its mean position, this O. Okay, so let's move to the conclusion that pendulum, hence the pendulum, which is simple pendulum, execute SHM, and its time period will be t is equals to 2 pi 1 over angular acceleration per unit angular displacement. Angular acceleration per unit angular displacement. And what is angular displacement per unit angular displacement? Is 1 over mu. Is 1 over mu. And what is the value of mu? As we discussed earlier, is 2 pi L over G. Is 2 pi root L over Z, because the value of mu, look at here, this mu has value G by L. Okay, so this, the time period of the simple pendulum which execute SHM is equal to t is equals to 2 pi root 1 over angular acceleration per unit angular displacement, and angular acceleration per unit angular displacement is mu. Okay, and what is the value of mu? As we discussed earlier, that t pi L over C, 1 over mu. Okay, because mu has value G by L, so L by Z, 1 over mu, L by Z. So the time period is equals to 2 pi root L by Z. Or simply you can say it by the analysis of this formula, that the time period of the simple pendulum is directly proportional to L over G, and G is because this experiment is performing on the Earth's surface, so G is constant, 9.8 meter per second square, 2 is constant, pi is constant, so only the thing which varies is the length of the string by which the simple pendulum is suspended by the rigid support. Okay, so this is the time period of oscillation of a simple pendulum which performing SHM. This simple pendulum which performing SHM, that's the time period. T is equals to 2 pi root L by Z, and there is only the variable quantity is this length, is only this length. Okay, so that's all for now, and meet you into the next one. Thank you.